Picture a steam locomotive so long it couldn't fit around its own railroad's curves. A Soviet monster that tore up the track with every single mile it rolled. A train with no wheels touching the ground at all, flying on nothing but magnets. For over a century, engineers chased power, speed, and size until they slammed straight into the laws of physics, and then tried to break them anyway. These 10 machines shattered the rulebook. Some triumphed, some destroyed themselves trying. Number 1. Union Pacific Big Boy. Let's start with the machine most people picture when they hear the word giant. Between 1941 and 1944, the American Locomotive Company built 25 of these beasts for the Union Pacific Railroad, and they earned the nickname Big Boy, supposedly scrawled in chalk on the smokebox by a shop worker during construction. The rule they broke was simple. A locomotive's rigid frame can only be so long before it can't get around a curve. Big Boy's answer was to cheat. It used a 4-8-8-4 wheel arrangement, 4 leading wheels, 2 separate sets of 8 massive drivers, and 4 trailing wheels, with the front engine hinged or articulated so the enormous frame could actually flex through curves. Nothing else on Earth ever used that wheel arrangement. The numbers are staggering even today. A Big Boy stretched about 132 feet 9 inches from the front coupler to the back of the tender and weighed roughly 1.2 million pounds. Its boiler ran at 300 pounds per square inch, and it could put down more than 135,000 pounds of tractive effort. These locomotives were built for one brutal job: dragging heavy wartime freight over the Wasatch Mountains between Ogden, Utah and Wyoming, climbing grades that would stall lesser engines. For years, they were the undisputed kings of the rails, with many logging over 1 million miles. But diesels and gas turbines eventually took over, and by 1962, every Big Boy was retired. Here's the twist that makes this one extraordinary. In 2013, Union Pacific reacquired number 40114 from a museum in Pomona, California, and spent years rebuilding it, even converting it from coal to oil. On May 1, 2019, after nearly 60 years cold and silent, 40114 moved under its own power again. Today, it's the largest operating steam locomotive on the planet, and when it thunders past, you understand exactly why people traveled hundreds of miles just to feel the ground shake. Number 2. Erie Railroad Triplex. Matt H. Shea. If the Big Boy bent the rules, the Erie Triplex tried to smash them with brute force and got humbled by basic physics. In 1914, the Baldwin Locomotive Works, working from a patented design by engineer George R. Henderson, delivered something never seen before: a locomotive with 3 sets of 8 driving wheels, not 2, 3. The first was named Matt H. Shea, after a beloved Erie engineer. 2 more followed by 9. The idea was pure ambition. More driving wheels meant more grip, and more grip meant more pulling power. To fit a 3rd set of drivers, Baldwin put them underneath the tender itself, so the coal and water car actually helped pull the train. In terms of raw tractive effort, it worked spectacularly. Estimates put the triplex at around 160,000 pounds of tractive effort, possibly the highest of any steam locomotive built up to that time. On paper, it was engineered to haul a train hundreds of cars long. And then reality showed up. The fatal flaw was steam. 3 sets of cylinders drank steam faster than the boiler could possibly make it. 1 firebox and 1 exhausted fireman simply could not keep up. Push the triplex past about 10 miles per hour and it would essentially run out of breath, its own boiler pressure collapsing. There's a famous account of the Matt H. Shea starting a train of 250 coal cars, and the run lasting just 17 miles before the sheer force of the pull literally ripped a coupler out of one of the cars and stopped everything. There was a second problem baked into the clever tender drive idea. As the locomotive burned coal and used water, the tender got lighter and its wheels lost grip exactly when you didn't want them to. The Erie gave up trying to run them on the open road and relegated all 3 to helper duty. Pusher engines shoving heavy trains up steep grades like Susquehanna Hill, where they could crawl at low speed and be refueled often. A similar, even less successful 4-cylinder version was built for the Virginian Railway, and it topped out at a heartbreaking 5 miles per hour. By the early 1930s, every Erie triplex had been scrapped. Not a single one survives. Number 3. Soviet Class AA20. Now we go to the Soviet Union in the 1930s, and to a machine so extreme it damaged the very ground it rolled on. Stalin-era Soviet industry was obsessed with gigantism. Bigger factories, bigger dams, bigger everything. So when engineers wanted more powerful freight locomotives that could still run on the country's relatively light rails, one group made a bold decision. Instead of spreading the weight over an articulated frame, they'd cram an unheard-of 7 driving axles into a single rigid frame. The result, built in 1934 with help from Krupp in Germany and the Vorshilovgrad works, was the Class AA20, a 4-14-4. Read that again. 14 coupled driving wheels, all locked into one non-bending frame. It remains to this day the only steam locomotive on Earth ever built with 7 driving axles in a rigid frame. The name honored Soviet official Andrei Andreev, and the 20 referred to its 20-ton axle load. Here's the iron law of railroading. It ignored. Rails are straight, but railroads are not. Every curve requires the wheels to shift and swivel. A short, rigid frame handles curves fine. But 14 driving wheels bolted rigidly in a line? That frame physically fights every curve it meets. The engineers knew this was coming, so they tried desperate fixes. They removed the flanges, the guiding rims, from the middle sets of driving wheels and gave the front and rear axles a little sideways play. It wasn't enough. The single locomotive, AA21, made a publicity run toward Moscow in early 1935, and in testing, it did exactly what the skeptics feared. It tore up track, it wrecked switches, it derailed on curves. Its pulling power was genuinely enormous, but it was fundamentally incompatible with the railroad it was supposed to serve. You cannot run a locomotive that destroys the track beneath it. The Soviets abandoned the second unit before it was even finished, having already chosen a more practical design. The one and only AA21 was quietly rolled into storage at a test facility near Moscow, where it sat, ignored for decades, a monument to overreach. It was quietly scrapped around 1960, and the experiment was never repeated by anyone anywhere. Number 4. Pennsylvania Railroad. S1. The Erie broke the steam rule. The Soviets broke the track. The Pennsylvania Railroad broke something almost poetic. It built a locomotive too big for its own railroad. In the late 1930s, the mighty Pennsylvania Railroad wanted a passenger locomotive that could scream across the flatlands at over 100 miles per hour, hauling long, heavy trains. Their engineers embraced a concept called the duplex drive. Instead of one big set of driving wheels, you split the power between 2 sets of cylinders on a single rigid frame. That reduced the hammering forces of the reciprocating parts, allowing higher speeds. The result was the S1, a single experimental locomotive numbered 6100, completed at the Altoona shops in early 1939. It used a 64-46 wheel arrangement that no other locomotive in history ever wore. And crucially, to stay stable at high speed, it was not articulated. Its enormous driving wheelbase was rigid. They handed the styling to the legendary industrial designer Raymond Loewy, and he wrapped it in sleek, streamlined Art Deco shrouding. The result was one of the most beautiful machines ever put on rails. So striking it became the centerpiece of the railroad exhibit at the 1939 New York World's Fair, where it sat on rollers spinning its 84-inch driving wheels at 60 miles per hour for the crowds. At about 140 feet, 2 inches overall, the S1 was the longest reciprocating steam locomotive ever built. And that was exactly the problem. That rigid, non-articulated length meant the S1 physically could not get around most of the Pennsylvania Railroad's own curves. This titan, built to conquer the network, was quarantined to a stretch of relatively straight main line between Chicago and Crestline, Ohio. On top of that, because so much of its weight rested on the leading and trailing trucks rather than the drivers, it was prone to slipping its wheels. It was too long, too heavy, and too specialized. The railroad had actually started work on a smaller, more practical duplex design, the T1, before the S1 even entered regular service. Number 6100 made its last runs in the mid-1940s, and despite its fame, was scrapped 1940s. There was only ever one, and none survive. Number 5. Pennsylvania Railroad, T1. The one not taught the Pennsylvania Railroad a hard lesson about size. So for their next act, They went smaller, sleeker, and faster, and stumbled into a completely different kind of failure. Meet the T1, a 4444 duplex. 2 prototypes arrived in 1942, followed by 50 production units in 1946, making them the last steam locomotives the Pennsylvania Railroad ever built. 52 machines in total. Once again, Raymond Loewy shaped the styling, giving the T1 a dramatic, sharp-nosed shark look that still turns heads in photographs today. They were fast, powerful, sophisticated, everything the railroad wanted. And they had a reputation for being nearly uncontrollable. The T1's signature flaw was violent wheel slip. Because it had 2 independent sets of driving wheels, if one set lost grip, it could spin wildly, sometimes at a standstill when starting a train, and sometimes, terrifyingly, at high speed. Firemen and engineers told stories of the driving wheels suddenly racing out of control. It was a locomotive that seemed to fight its own crew. For decades, that made the T1 a symbol of the duplex idea's fundamental weakness. Proof that splitting the drive was a beautiful mistake. But here's the fascinating rule-breaking twist. And it's a twist about people as much as machines. A detailed study published in 2008 by the Pennsylvania Railroad Technical and Historical Society argued that the wheel slip wasn't really the design's fault at all. The problem, the research suggested, was training. The T1 was so much more powerful than the engine's crews were used to that many engineers simply applied too much throttle too fast, overwhelming the grip and triggering the spins. In other words, the machine may not have been broken. The humans hadn't caught up to it. By then, it didn't matter. In 1948, the Pennsylvania Railroad committed to dieselizing all its express passenger trains, and the T1's flaws, real or human-caused, would never be fully resolved. Every single one was scrapped, and yet the T1 refused to die completely. A group called the T1 Trust is currently building a brand new T1 from scratch, locomotive number 5550, decades after the last one was cut up, hoping to prove what this stunning, misunderstood machine could really do. Number 6. Chesapeake and Ohio M1 steam turbine. By the late 1940s, the diesel locomotive was clearly winning. But the Chesapeake and Ohio Railway made most of its money hauling coal, so abandoning coal-fired locomotives felt like betraying its own customers. Their solution was one of the strangest machines American railroading ever produced. Working with the Baldwin Locomotive Works and Westinghouse, the C&O built 3 enormous locomotives, numbered 500 to 502, delivered in 1947, 1948. They were classified M1, and they were steam turbine electrics. Coal and water made steam. The steam spun a turbine. The turbine drove generators, and the electricity powered traction motors on the axles. Essentially, it was a power plant on wheels. Almost everything about it broke convention. To start with, it was built backwards. On a normal steam locomotive, the coal and water ride in a tender behind the cab. On the M1, the coal bunker was up front, and the boiler was in the rear. Passengers and crew looking at it could be forgiven for not knowing which end was which. It was also colossal. When it was built, the M1 was the longest single-unit locomotive in the world, weighing around 857,000 pounds and producing roughly 6,000 horsepower, with a boiler pushing 310 pounds per square inch. The logic was seductive. A turbine has fewer pounding, reciprocating parts than a piston engine, so in theory it should need far less maintenance. Its designers even claimed it could run a long round trip without servicing. Theory and reality once again refused to shake hands. The M1 was built for a specific reason, to pull a glamorous new streamlined passenger train called the Chessie. But the railroad canceled the Chessie in 1948, before it ever carried a paying passenger. In one stroke, these 3 magnificent, complex, hugely expensive machines lost the entire reason they existed. Left without a purpose, they proved exactly as troublesome as skeptics expected. Mechanically unreliable and brutally expensive to operate. They rattled around in limited service in Virginia and lasted barely long enough to embarrass everyone involved. All 3 M1s were scrapped by 1950, just 2 to 3 years after they were built. It stands as one of the last and boldest attempts to keep coal-fired steam alive, and it failed almost instantly. Number 7. Union Pacific gas turbine. Big blow. If the C&O's turbine was a quiet failure, The Union Pacific's turbines were the loudest success in American railroad history, literally. Union Pacific ran enormous freight across long, empty stretches of the American West, and it wanted raw, overwhelming power. So it turned to an idea borrowed straight from aviation, the gas turbine. General Electric, which had been building jet engines, proposed putting essentially a stationary jet engine on a locomotive to spin a generator. Union Pacific went all in, eventually operating the largest fleet of gas turbine electric locomotives of any railroad on Earth. The ultimate version arrived between 1958 and 1961, 33rd generation units, and they were monsters. Each one produced 8,500 horsepower from a single turbine, the most powerful prime mover ever installed in any North American locomotive, a record that still stands to this day. In cooler, denser air, the turbine itself could theoretically exceed 10,000 horsepower. They held it back only because the electrical system couldn't safely handle more. They earned the nickname Big Blows, and the reason was their sound. When one of these turbines spun up under full load, it shrieked exactly like a jet airliner, blasting hot exhaust out of roof vents. They were so deafening that Union Pacific mostly kept them out in the empty country between Council Bluffs, Iowa, and Ogden, Utah. When tested toward California, cities were so unhappy with the noise that the turbines became deeply unwelcome there. At their peak, these turbines hauled more than 10% of the entire railroad's freight. Each locomotive was a three-piece set: a control unit, a turbine unit, and a fuel tender, stretching around 179 feet and weighing nearly 850,000 pounds. And here's where the design got wonderfully weird. To save money, they burned Bunker C, a heavy fuel oil so thick it has the consistency of tar or molasses at room temperature. It literally had to be heated to around 200 degrees Fahrenheit just to flow into the turbine. Several of the fuel tenders were actually rebuilt from old steam locomotive tenders. The turbine's great weakness was appetite. They guzzled roughly twice as much fuel as a comparable diesel. As long as Bunker C stayed cheap, that was fine. But as costs rose and reliability problems mounted, the economics collapsed. By 1970, every last Big Blow was retired. Two survive in museums, silent reminders of the days a jet engine hauled boxcars across Wyoming. Number 8. East African Railways 59 Class Baya Garat. So far, we've watched engineers fight the curve versus power problem, and mostly lose. Now let's meet the design that arguably solved it more elegantly than anyone, and it came from a surprising place. The concept is called the Garrett, named after its inventor Herbert William Garrett, and the first one was built back 1909. The idea is brilliant. Instead of stuffing everything onto one frame, a Garrett splits the locomotive into three parts. Two completely separate engine units sit at the front and rear, each with its own set of driving wheels. Slung on a cradle between them is the boiler and cab. The water rides over the front engine, the fuel over the rear. Why is that genius? Because the heavy boiler no longer has to sit directly on top of the driving wheels. That frees engineers to build a huge, fat, free-steaming boiler. The two engine units pivot independently, so the whole enormous machine snakes gracefully through tight curves. And because the weight is spread over a long wheelbase, a Garrett can run on light, cheaply laid track and cross fragile bridges that would collapse under a rigid giant. One Garrett with one crew could replace two conventional locomotives with two crews. The masterpiece of the type was the East African Railways 59 class. 34 of these oil-fired giants were built by Bayer, Peacock in Manchester, England, and they entered service in 1955-1956. Their wheel arrangement was 482 plus 284, essentially two mountain locomotives working back-to-back. And here's the detail that stuns people. They ran on meter-gauge track, rails just over 3 feet apart, narrower than standard railroad track. On that narrow gauge, they were the largest, heaviest, and most powerful steam locomotives in the world. Each weighed around 252 tons, carried a boiler 7.5 feet in diameter, and delivered a colossal 83,350 pounds of tractive effort. Their job was to haul 1,200-ton trains up steep grades on the 330-mile line from the port of Mombasa to Nairobi. Each was named after an African mountain, and their crews, many of them Sikh drivers, kept them so immaculate that one photographer said a 59 class cab gleaming with polished brass and mirrors looked more like a temple than a locomotive footplate. They ran until 1980, and a couple are preserved in Kenya to this day. This is what breaking the rules looks like when you do it right. Number 9. The Bennie Railplane. Every locomotive so far has done one thing in common: run on rails, on the ground, pushed by cylinders or a turbine. Our ninth machine threw out nearly all of that at once. In the 1920s, a Scottish inventor named George Bennie looked at the slow, smoky trains of his day and imagined something radically different: a high-speed passenger vehicle that didn't sit on the tracks at all, but hung above them. He called it the railplane, and it looked like a cross between a train, an airship, and a fighter plane. The railplane was a sleek, cigar-shaped car suspended from an overhead monorail, steadied by a guide rail below. But the truly wild part was the propulsion. It had no conventional engine driving its wheels. Instead, it was pushed by aircraft-style propellers, one at each end, spun by electric motors. It was, essentially, an aeroplane that flew along a rail. Bennie's vision was clever. Build these overhead gantries above existing railway lines, and fast railplanes could zip passengers overhead at high speed while slow freight trundled along the tracks below. No conflict, no congestion. He claimed the railplane could reach 120 miles per hour, a fantastical speed. 1930. To prove it, between 1929 and 1930, he built a full demonstration line at Milngavie, near Glasgow. An elevated test track, a little over 400 feet long, running above an existing railway siding. The luxurious carriage was built by William Beardmore and Company, a firm that had actually built airships, and it showed. The interior was plush, the ride smooth and quiet. On July 8, 1930, the press and public were invited to ride, and they were genuinely impressed, hailing it as the future of transport. But the future needs funding, and Bennie never got it. The test track was short, so that dazzling 120-mile-per-hour claim could never actually be demonstrated. Cautious transport authorities weren't willing to bet on something so unproven. Bennie poured his own money into the dream, chasing proposals for lines from Blackpool to the Middle East, and it all came to nothing. He was declared bankrupt. 1937. The strange, beautiful railplane sat rusting above that Scottish field for more than 2 decades before it was finally sold for scrap in 1956. George Bennie died the following year, in obscurity, an inventor whose flying train was simply too far ahead of its time. Number 10. The TGV V150 and the Maglev L0. We've saved the ultimate rule for last. Every locomotive in this video, from the big boy to the railplane, obeyed one fundamental limit: how fast can you go with wheels rolling on rails? For our final entries, engineers took direct aim at that limit, and one of them abolished it entirely. First, the wheel's last stand. On April 3, 2007, on a brand new high-speed line in eastern France, a specially prepared French TGV, codenamed V150, launched down the track. This was not a normal train. Engineers had stripped it to just 3 double-deck cars between 2 power cars, fitted it with oversized wheels over a meter across, borrowed more powerful motors, and even boosted the overhead line voltage from the usual 25,000 volts up to 31,000 to force more power into the motors. It made nearly 20 megawatts, enough to power a small town. As it screamed across the countryside, chased by an aircraft relaying live data, the V15 hit 574.8 kilometers per hour. That's 357 miles per hour. At that speed, its wheels were spinning at nearly 3,200 revolutions per minute. It was, and remains to this day, the fastest a conventional wheeled train has ever gone on rails. It proved that steel wheel on steel rail could survive 357 miles per hour, but it also showed just how much extraordinary effort that final push demanded. This is the absolute ceiling of the wheel. So engineers did the only thing left. They got rid of the wheels. On April 21, 2015, on a test track in Yamanashi, Japan, a train called the L0 series did something no locomotive on this list could dream of. It reached 603 kilometers per hour, 375 miles per hour, making it the fastest rail vehicle ever built, and it managed that with nothing touching the track at all. The L0 is a superconducting maglev, short for magnetic levitation. Powerful magnets lift the train clear off its guideway and propel it forward, so there are no wheels, no rolling friction, no contact whatsoever. The single rule every other machine in this video had to obey, wheels grip rails, simply doesn't apply to it. That's the perfect place to end. From the big boys shaking the mountains with 1.2 million pounds of steel and steam, to a Japanese train floating on magnetic fields at 375 miles per hour. This is the story of engineers who looked at the rulebook, decided it was more of a suggestion, and changed what a train could be. If you made it to the end, drop a comment telling me which of these machines you'd most want to see in person. And if you'd ride the propeller-powered flying train, you're braver than me.